Hi, I'm Scott Vaughn. This is a video on the mathematics of navigation. This is part 2 in a series on that I've called the Starship Moon Landing. In part 1, I studied the flight path angle and pitch of a spacecraft on its way to the moon. In this part 2, we'll study the mathematics of navigation on the moon. In this video, we'll derive a formula for Rhumb line bearing and Rhumb line distance. And the mathematics in this video apply directly to navigation in real life. First on Earth, but also on the moon and on Mars. Particularly useful now for the Artemis mission to the moon and for the many rovers and now the helicopter on Mars. These principles apply on any spherical planet or moon anywhere in the universe. What we develop and apply here in this video are quite literally universal principles of calculus, trigonometry, and spherical geometry. This is really fun because I've learned so much more math and physics after discovering this game Kerbal Space Program, and I've taught math for many years. Of course, calculus was invented specifically for the purpose of understanding the motion of objects in a gravity field, and KSP gives us this perfect textbook virtual lab to study those principles. In fact, in part 1 of this series, I launched a starship to the moon in KSP and used that to illustrate principles of the calculus of parametric and polar equations, with an example involving the flight path angle and pitch of the starship as it travels to the moon. In this video, we'll pick up after the landing of that starship, and thanks to Matt Lown, by the way, for this recreation of the SpaceX moon lander. And calculus is useful for, of course, much more than just describing the motion of objects in a gravity field. The topic of navigation can also be studied with calculus and KSP. And for me, I've gained a much deeper understanding of spherical geometry and trigonometry with KSP. Piloting a plane to the North Pole or the South Pole on Earth isn't something I'm likely ever going to do, and much less navigating a lander to the South Pole of the moon. But because I can do these things in a simulation in KSP, I've gained a much better understanding and intuition for these mathematics applications. And when it comes to explaining the abstract tools of trigonometry and calculus in class and how they are applied when individual math topics are introduced in an academic program, they're typically presented devoid of their original applications. But when the purpose of those tools can be highlighted, it's always helpful. It's important to be able to learn abstract concepts in their own right, but we can all better appreciate a tool when we can see how that tool is used. So then let me next say just a little bit about the difference between Rhumb line versus great circle paths in navigation. And then we'll do this derivation of the Rhumb line bearing, the direction you would travel to maintain the Rhumb line path. And we'll also derive the distance formula for Rhumb line navigation. And then some examples. Of course, I have a perfect tool for illustrating those principles. And while I demonstrate this in Kerbal Space Program, this is exactly applied in real life, both on Earth, on the moon, on Mars, on any spherical planet or moon. So the great circle path is the shortest distance between 2 points on the surface of a sphere. The great circle path is a straight line on that curved surface of the sphere. And the Rhumb line path is the path with a constant heading, or azimuth. That azimuth is an angle measured from north to the direction of the ground track or the path. So when we say heading, that's the direction you're pointed, and bearing is the direction that you want to go. And the Rhumb line turns out to be a straight line when projected onto a two-dimensional map. On the curved surface of the sphere, the great circle is the straight line path and the shortest distance, and it's the Rhumb line that appears curved. But on the flat surface of a two-dimensional map, the great circle appears curved, and the Rhumb line is the straight line path. Generally, the Rhumb line distance is greater than or equal to the great circle distance. This is a really fun and interesting website, cavas.com, which illustrates both the great circle and Rhumb line paths on the two-dimensional map of the Earth. So we can move these points about, and you can see the great circle here being curved when it's on the two-dimensional map. And as I move these points around, you can see how the Rhumb line is a straight line and looks like the shortest path, but that's when you're projected on a two-dimensional map. But in fact, the Rhumb line is actually generally the longer path. It just looks shorter when you project the curved Earth or curved sphere onto a two-dimensional map. When you're on the equator, the Rhumb line and the great circle are the same, and when you travel directly north and south along lines of longitude, the great circle and Rhumb line are the same. There's really an interesting sideline here on the topic of flat Earth. Unfortunately, spherical geometry is rarely covered in math in school. We spend so much time working on the flat Euclidean geometry of the plane. In fact, we write our work on flat pieces of paper and on flat computer screens, and teachers do their presentations on a flat chalkboard or whiteboard or PowerPoint screen. And we always look at flat projections of the Earth on 2D maps when you're searching, for example, on Google Maps or Apple Maps. No wonder so many people have fallen into the idea that the Earth is flat. In math, we work so hard on these very simple ideas of the flat Euclidean geometry, but maybe it's boring for some students. And it doesn't capture their imagination. As educators, we follow this standard curriculum that you have to cover flat Euclidean geometry before you can learn spherical geometry, and many students just bail out before they ever get to the spherical geometry, something that's really finally covered starting in Calculus 3. So while this video is a lesson in calculus and even some beginning differential equations and is made for students in calculus, Kerbal Space Program illustrates these topics in a way that is accessible to anyone. Just like you don't need to know every detail about how the engine of your car works in order to drive, you don't need to know all the math to calculate direction in navigation. But understanding the math of navigation helps understand how it works, how to communicate with those that design navigation systems, and to understand a little bit better what to do if they failed. Okay, so now I'm ready to do the math behind the derivation for Rhumb line bearing, the direction you go to follow the Rhumb line path. Now, I've already done a video on the great circle, the derivation of the formulas for great circle distance and heading. So won't do them here, but I will make references as I go along to the great circle path, so I wanted to make sure that the distinction was clear before we got further into this. Okay, so then in the notes that I have written here in this derivation, I'm going to use theta to represent latitude, and the angle phi represents longitude. So obviously here I have a two-dimensional map and the three-dimensional sphere with a radius of r. It could be the Earth, the Moon, Mars. It could be Kerbin or Kerbin's moon called the Mun. This could be the entire sphere just stretched out into a two-dimensional map, or it could be just a portion of it. It doesn't really matter in this derivation. So what you see here, obviously, if we focus on the 2D map for a moment, we've got a point A where we'll imagine we begin and we want to get to a point B. So from point A to point B, there's some change in the latitude from latitude at point A to latitude at point B, and from longitude at point A to the longitude of point B. So we'll have some change in longitude as well. So when we talk about this Rhumb line heading or Rhumb line bearing, that's the angle that I'm going to call alpha. This is an angle that is measured relative to north. So directly up to the top of the page in the 2D map is north, and this is the direction we want to go. So it's the angle between north and the direction that we want to go. That's the angle alpha. That will be the answer. That is what we're trying to figure out. What direction do you go to reach the destination? And in the case of a Rhumb line, you stay with that heading. Whatever that initial bearing is, you turn your heading to be in the direction of that desired bearing. So again, bearing is the direction you want to go, heading is the direction that you're looking. So you look, you set your heading to that particular bearing, and then you just maintain that constant heading for the entire trip in the case of a Rhumb line. All right, so when we're trying to find alpha, what we can now do is, as you can see, I've got this triangle that I can imagine on the two-dimensional map. And what I'll need to do is figure out each of these distances, and through calculus and integration, I can actually find this angle alpha. I'll derive it. So let's say first, let's figure out, why do I have this r d theta here? So the r d theta is, well, it corresponds to, first of all, the radius of the sphere. So here I have a picture of the sphere that I can use to explain how I get that factor r d theta there. So it really comes back to the very beginning definition of a radian in the beginning of trigonometry. At the beginning of the trigonometry class, we say that this angle, which I've called d theta, some change in the two latitudes, right? So that's latitude at point B, that's the latitude at point A. If we're traveling from point A to point B, if we go north or south, if we have a change in our latitude, then that's what the d theta would be. It's the difference in those two angles. So this angle d theta is this arc length divided by the radius of the sphere, s divided by r. That's d theta. That's the definition of a radian. So solving for s, it would be r times the differential in theta, or the differential or the change in the angle. So that's r d theta. That's why I'm going to say when I map the sphere onto the two-dimensional map, this distance here will be r times d theta. It will be the sort of vertical distance on the map that corresponds to that change in position in terms of the change in the latitude. So the next thing I'll explain is, how do I get this length over here on this side of this triangle in the 2D map, d phi r cos theta. So I have some difference in the longitudes, longitude at point B and longitude at point A, and subtract them, and I get this differential change in the longitude. But as you change latitude, this distance becomes smaller or larger depending on whether you're going north or south because of the curvature of the Earth or sphere. So here I have the angle theta that actually represents the latitude, right? So the latitude, here's the center of the sphere, drawing straight out to a point midway between north and south. I have the equator. So here's the equator going around the sphere. And here, with a radius of r, I have a circumference of 2 pi r. That's the distance all the way around the sphere. But as you go further north and further south, these lines of latitude are smaller and smaller and smaller as we approach the poles. So what is the radius of these smaller circles? Well, that radius is basically this length right here. It's the same length here as it is down here. And how do I get this distance? What I'll do is I'll say that the cosine of that latitude is the adjacent side over the hypotenuse of this triangle that is contained within the sphere. Cosine would be the adjacent divided by the hypotenuse. In this case, the adjacent, I'll just momentarily call that A, and say it would be that distance A divided by the radius, because this is from the center of the sphere out to a point on the sphere. So that's radius r. And if I solve for A, once I have that relationship between the latitude and that distance a and the radius of the sphere, I can solve for a. So that distance there, a, is r cos theta. In other words, the radius of these circles of latitude gets smaller as you go further north and south from the equator based on this factor of the cosine of the latitude. So it scales with the cosine of the latitude. Cosine is always less than or equal to 1. And in this case, I can go from an angle of 0 at the equator up to 90. And let's say in this explanation, I'll just say from 0 to 90 as you go south, so that I'm keeping the cosine value positive. And so that's where I get this factor of cosine theta there. So this distance here would scale with the radius of the sphere, so it's the differential in the longitude times r. Just for a minute, imagine that it was the difference in the angle was 2 pi, one complete rotation of 2 pi radians. That would be 2 pi r, and that would be the entire circumference. If you had 2 pi as the difference between those two angles, you would have 2 pi r, you would have a distance of 2 pi r, you would have the circumference. But as you change the angle theta, you scale this length by the cosine of the latitude. So I don't necessarily mean cosine at b right here. What I mean is that I'm actually going to allow the angle theta to vary between this point and this point in a process of integration and add up values. So the theta that I have here is any angle in between those 2 points. So it scales with the cosine of the latitude, whatever the latitude might be between those 2 points. So it's this equation that we use first to derive the Rhumb line bearing. I haven't finished that yet. I still need to solve for alpha, and I have to do some integration in order to be able to do that. But that'll be the first derivation, using this relation to derive the Rhumb line bearing. And the other thing that we can get from that diagram is this relationship, which I'm going to use to calculate the Rhumb line distance, or to derive. And so that's what I'll use to derive Rhumb line distance. Let me show you where this comes from. I think I can have this all on the screen at the same time. When we talk about the cosine of alpha, that's the adjacent side over the hypotenuse. So the hypotenuse I've labeled dx. It's a differential amount of distance, and what I'll end up doing is integrating over that entire distance to actually find the distance, integrating from point A to point B to get the total amount, the total distance. Relationship between the cosine of alpha and the differential in the theta and the differential in x that allows me to use integration to find that length. So yes, the adjacent side, r d theta, divided by the hypotenuse, dx, and as we integrate with respect to theta and x, we'll be able to solve for x. Okay, so then let's start with this equation that relates the Rhumb line bearing with change in longitude and change in latitude, and we'll solve for alpha. So alpha is that Rhumb line heading, and in order to solve, I actually have to, and to be able to write it in terms of the given latitude and longitude of the 2 points, I need to integrate. I need to solve for expressions for both phi and theta. So this is literally a differential equation in the differentials in longitude and latitude. And so this could fit right into the beginning of a differential equations class. All I'm really doing is Calc 2, really the beginning of Calc 2 as well, just basic integration. So what I need to do here is rewrite this equation so I can integrate both sides. In the differential equations class, at the beginning, that's the first topic. It's called separate variables. So that's what we'll do here. We'll just rewrite this so that our differential is not in the denominator. So I'll say tan alpha times differential in theta is cos theta times the differential in phi. And because this is cosine of theta and this involves theta, I'll put this factor over on the other side, and because this is a constant, it doesn't really matter what side it's on, but it'll be convenient to write it on the other side. So we'll end up with 1 over cos theta d theta is 1 over tan alpha d phi. It's at that point that you could just say integrate both sides. So that's what that represents. So what I'm doing is I'm integrating over the change in the latitude here. So that is from latitude at point A to latitude at point B, and on the right-hand side, I'm integrating over the change in the longitude. So that's longitude at point A to longitude at the terminal point B. Well, let's take this side first. We're looking at 1 over cosine, and that's secant. So this means I have theta A to theta B integral of secant theta d theta equal, and actually this is differential in phi, and that is tangent of alpha, which would be constant over the change in the longitude. So you can factor that guy out. It's a constant. Alpha is a constant, so the tangent of alpha is a constant, and it then looks like this. So now we need the antiderivative for secant, and that's in the Calc 2 class, and usually hard to find applications of that. This is it right here. The antiderivative is the ln of secant theta plus tangent theta. I'll leave that for your calculus teacher to prove. So we'll say evaluated at theta A and theta B, and then on the other side, this is actually a really easy integration because that's just a factor of 1 there. So you could just say 1 times the length of the interval, or just phi and then plug in the bounds. What you end up with, very simple here on the right-hand side. All right, now this next thing that I want to do is I want to rewrite this. Not that I necessarily particularly have to, but what I could do is write this. Actually, what I want to do is just write this secant theta tan theta as just the tangent of theta over 2 plus pi over 4. Again, don't have to, but exactly at this moment, it just reminded me that I wanted to say something earlier, that all these angles must be in radians. Part of that is you can see right here, you can't measure this in degrees and expect it to equal the result there. But perhaps even more fundamental, all the way back at the beginning, I should have said that right there when I was explaining what that d theta represent, I said it came from the definition of radians. If you're going to say that that change in the angle is the arc over r, the arc length s over r, then that has to be radians. This has to be d theta. The angles have to be measured in radians. So if we have normally, of course, it's going to be degrees when you're talking about latitude and longitude. So we have to convert it to radians. Another place where I could have made that comment was when I was talking about how whatever this was, suppose, for example, it might be 2 pi. And if that distance was 2 pi, then the distance between those would be the entire circumference, 2 pi r. So once again, I had the opportunity to say that the angles for the latitude or longitude, while they're given in degrees always, in practice, we have to convert them to radians for this calculation. And that reminded me right here when I saw that pi over 4 as an angle added to whatever angle you might be working with divided by 2. And actually, I don't really have to make this conversion, but it's slightly nicer to have the angle show up only once rather than twice, because you've got you've got 4 angles, right? The latitude, longitude at the start, latitude, longitude at the end, and if you can reduce this down to just one place where you write it, it's slightly preferred, and it's very likely that if you Google search for a formula for Rhumb line bearing, you'll see it written this way rather than that way, and I'm not sure why that is. Maybe just because it's a little bit simpler to have the angle refer to only once. So I'm going to replace that with this. In order to do it, I'm going to show that that is actually equal to this. And this is the sort of thing that you would assign in a pre-calc class as an identity, a trig identity that you have to prove always true. So that means that you start on one side and do all of the algebra and trig that you can use to show that it's always equal to that. So this just looks like that very arbitrary sort of exercise that we would do in the pre-calc class. And so I want to include that here as just this is more application for those kinds of exercises that we do, standard things that we do in the pre-calc class. But I'm going to run through this one quick because it really is well, a little bit off on a tangent, but it's beautiful. So watch this. I'll say this is the left-hand side and this is the right-hand side. I'm starting with the right-hand side. Right-hand side. And I'm going to show that that's equal to the left-hand side. So we've just showed that this right-hand side is actually equal to that left-hand side. So we can replace that with this expression. So we'll write ln, absolute value of the tangent of theta over 2 plus pi over 4, where now it's clear that it's a reminder that the angle's in radians. So because these are equal, we can just replace that. And now, finally, we can solve for tan of alpha, and therefore alpha, in terms of the initial latitude and initial longitude. Actually, first what I did here is I plugged in the bounds. Fundamental theorem of calculus. So now I have an expression that relates latitude and longitude and the Rhumb line bearing. So let's solve for the Rhumb line bearing. We can combine those two ln's into one. That's a property of the natural log. So there it is. That's basically it. And one last step would also be that you could take tan inverse. However, the issue with the tan inverse is that by definition it's restricted to angles from -90 to +90, and we can actually have bearings that go past 90 degrees all the way around to 360. And we want to measure relative to north. So we need to do some modification in the output, just like I did exactly the same process in finding the great circle bearing. All right, so that's basically the formula that I will then plug in some numbers. So I'll now do an example, and the example that I'm going to do is a calculation that I'll then demonstrate in Kerbal Space Program, going from a point at the south pole of the moon up to another point near the equator. So I'll do an example with these 2 points, and the first thing I got to do is convert it to radians. So the example that I'll show the work for is this one. From point A to point B, I've got 70.96 degrees south, 68.14 degrees west. I'm traveling to 22.5 north, 46.46 east. We need to convert these angles into radians, and note that any latitudes that are south or any longitudes that are west will be negatives in the calculation. So here is point A converted to radians, and this is south and west, so they're both negative. This is the point B converted into radians, and then I just plug that into that formula. It's pretty cumbersome formula. Absolutely, this is something that you want to just program into the computer, which I will demonstrate in Excel. But if you do it by hand, you come out with an expression about 0.91 inside the tan inverse, take tan inverse and make sure it's in radian mode. You get about 0.74 radians, and that's 42 degrees. Now, that's a pretty satisfying answer. It is, after all, the answer to life, the universe, and everything, and it's also the constant heading that I need to fly from the UFO at the South Pole on the Mun back to the moon base where I landed that Starship. So 42 degrees is the angle that I need to fly. So I have put this formula into Excel, and I'll do this calculation now on Excel quickly without having to write it all out, and just navigate around a few places on the Mun to find some of the interesting points around the Mun, just because it's fun on the Mun. Oh, hold on. We're almost done. I'm almost done. But there's also the Rhumb line distance, and this is actually a simple one. This is much quicker. Let's derive the formula to calculate distance as well for the Rhumb line. And of course, I have that programmed into Excel so that it runs very quickly on the computer, and I will demonstrate both bearing and distance. Yeah, so let's derive the actual formula for the distance. So I'm using this as my starting point, which I had derived again, earlier as the cosine, this differential adjacent over hypotenuse, this differential divided by that differential. So we can solve for x in terms of change in latitude. So we can take this differential equation and separate variables again. Let's write cosine alpha differential in x equal r times differential in theta, and then just integrate both sides. On the left-hand side, we're integrating from some initial point x1 to some initial point x2, like the point A to point B. And on the right-hand side, we're going from the initial latitude, theta A, to the terminal latitude, theta B. And both of these integrals, this is constant with x, so you can factor that out. You get cos alpha, and the r is a constant, factor that out. And these integrals, this is cos alpha, and this is x2 minus x1. That's your total distance, change in your position. And this is theta b minus theta a. The distance is the total integration of all that differential in position. It is the distance the distance between x1 and x2. So that's it. That's how I calculate the distance. That's actually pretty simple, right? You just get the difference in the latitudes, but they have to be in radians. It's kind of clear again that this couldn't be in degrees when you're multiplying by the radius and dividing by this and expecting it to get a distance. You need to have the difference in the latitudes in a dimensionless unit, so it has to be converted to radians. But so there it is, the distance for the formula for the Rhumb line distance. Pretty simple. It's just the radius of the planet or moon multiplied by the difference in latitudes between the starting and ending point and divided by the cosine of the Rhumb line bearing. Interesting how it works out that way. All right, I put that into Excel for several different points navigating around the Mun. Let's do that. It's pretty fun. All right, so now to handle every possible situation, there are some minor details that I kind of glossed over a little bit in the derivation. For example, in Excel, I have to use the 2-argument arctangent function rather than just the standard tan inverse for angles that are greater than 90 and less than negative 90, because by definition, tan inverse isn't, those are outside of the range of the tan inverse. And also for angles that are negative, I have to convert those to angles between 0 and 2 pi. But what we saw there in the derivation and that one example that I did working out by hand, that's essentially what's going on in the Excel sheet. fact, you can see that answer right here, this 42 degrees for the trip from the UFO back to the Moon Base 1. So let's go through now from the Moon Base 1, where we actually started, where the Starship landed. We'll fly to the Armstrong Memorial. So you'll see that I'll try to maintain about 226, 27 degrees constant heading. Again, here's the latitude and longitude of where I'm starting and latitude and longitude of the target location. So it's not really that far. It's going to take about 3 minutes if this was my average speed in meters per second. Okay, so here we go. And you can see that I have Waypoint Manager over here on the left showing the destination that I'm trying to get to, the Armstrong Memorial, and its latitude, longitude. Remember, my desired Rhumb line heading is about 227 degrees, and you see the little yellow circle is actually the direction that I'm actually traveling, and that little orange V, that is the direction that I'm pointing. And so I will sometimes be adjusting the thrust so that I can sort of move the direction in which I'm traveling onto this desired 227 degrees. Now, Waypoint Manager actually tells me the Great Circle path, which is, in this very short trip, really no difference. Next, I wanted to see the UFO buried at the south pole of the Mun, but that was a pretty long trip, and knowing the Great Circle path is faster, and it is the direction given by the Waypoint Manager in KSP, that was just easier to follow. The Great Circle initial heading from the Armstrong Memorial to the UFO is about 199 degrees. You'll see I stay pretty close to 200 degrees in this trip. And as I think about the real-life NASA Artemis mission planning to land at the south pole of the moon in search of water, I myself am learning some interesting lessons about navigation without an atmosphere. I expected the Rhumb line path to be easier, just maintain the same constant heading. But here I'm flying to see a UFO, again, discovering something true in reality. Maintaining a constant heading means continually turning, and each burst of thrust can add speed to the point where I'm risking reaching orbital speed, and each additional correction requires more speed, and things quickly escalate to the point that I'm off course. So flying an airplane in an atmosphere on Kerbal or Earth, it was much easier to maintain a constant heading. The control surfaces of the airplane's wing provide a way to turn without gaining speed, and the air resistance and drag just keep the speed from continually increasing with each correction. So I learned that in an atmosphere, Rhumb lines are easier to follow, but with no atmosphere, because the Great Circle path really is the straight line path along the surface. That's actually easier to follow, as it requires less turning. So now I want to get back to base, my moon base 1, where I landed the Starship and started this whole tour. But I'm still really interested in comparing Rhumb line paths and Great Circle paths. And I've already made 2 videos on Great Circle paths, both the derivation and application. And this video is clearly long enough, so I won't go into all that detail here. But those flights with the Great Circle path were on Kerbin with an atmosphere where maintaining a constant heading was easier. So here we are watching the Kerbal X lander fly pretty much straight as the heading is changing. The angle we face relative to north is changing. In an atmosphere, I would have considered this more difficult because clearly I want to make sure I'm still on the correct heading. Here I'm just using Waypoint Manager to confirm I'm on the correct heading, and only a few occasional thrusts are required to correct the path. But because this whole video has really been about the Rhumb line path, I wanted to make that same flight again, this time following the Rhumb line heading from the UFO back to the moon base, which I had calculated to be about 42 degrees. If my math was correct, I should be able to return from the UFO to base following that angle that is numerically also the answer to life, the universe, and everything, 42 degrees. Well, it does work, but it was quite a challenge. When we think constant heading, if you are thinking of a flat surface, you don't expect to be turning. But on the curved surface of the sphere, the constant heading does require turning. And turning with no atmosphere is a lot more difficult. Consider turning on a road with good tires that provide friction versus turning on ice. When there's no atmosphere on the Mun, there's no friction on which to provide, make it easier to turn. So after many attempts, I got back to base. It was a challenge, but it was really fun and really a fascinating learning experience for me. I did the math, I checked my answer with a video game, and the principles I learned here are vital to NASA's Artemis mission to establish a permanent moon base and explore the southern pole of the moon for water and other resources throughout the moon. Okay, that's it. That's the end of the video and the end of the tour. A tour of the Mun and the mathematics of navigation. Thank you for watching, and I hope you learned some math and some navigation. In part 3, we'll return to Kerbin and study the conic sections, ellipses, parabolas, and hyperbolas, and how they relate to orbital mechanics. If you like this video and want to learn more math with KSP, check out my website, sites.google.com, view KSP Math, where I've posted a lab workbook I am writing on math and physics inspired by KSP, along with other videos and interactive graphs and downloadable Excel files such as the Great Circle and Rhumb Excel files that I used in this video. Also, thanks to Matt Lown for his recreation of the SpaceX Moonlander. And thanks to all the artists who posted work on Free Music Archive. I've had so much fun adding music into this video. And finally, thanks to the developers and programmers and all the employees at Squad and Private Division for producing and continue to develop and improve Kerbal Space Program. It's amazing how this game has inspired me to discover and learn new topics in math and physics.